Okay, now it's recording. Okay, so what we are doing now is we are going to see what is the effect of external strain on rotation of individual line segments, right?
Yeah.
The members we consider as line segments. Now, now you remember that if you have two line segments, change in angle between them is nothing but shear strain, right? You remember this, right? So if you have two line segments, stop share screen. Can you see?
Yes, I can see it. Yes.
Right? This
Yeah.
this thing you remember. So now the only thing is okay, again here the notation and the thing may trouble you, but what we are doing is here is a unit vector after deformation, and the unit vector, it is n bar. The unit vector before deformation was n, right?
Okay.
Now if you have two vectors, right?
Yes.
Magnitude of A cross B is AB sine theta, right?
Yes.
When theta is small, then sine theta is approximately theta, right?
Yes.
Okay, so now take, this is n. So when you have two unit vectors, n is before deformation and hat is after deformation, right?
Yeah.
Then when you take n cross n hat, you are getting this angle alpha, right? Which is the rotation.
Okay.
Now, I remember one thing, this will include even rigid body rotation. So do you remember from mechanics of materials this thing that, just a second. must have written it here. Yeah, it's there here, the figure. Okay. So you can see this figure here. This is gamma. This is shear strain. If you have a theta 1 and a theta 2, gamma is theta 1 plus theta 2, right?
Yeah.
Okay. But now,
How did you get it? Pi divided by 2. That's 90 degree.
yeah, pi by 2, right?
Yeah.
Okay. So this theta 1 plus theta 2 is gamma in the second figure, right?
Yes.
Yes. Now, if you take yeah, like this. Okay, this example is maybe easier to see like this. Like this. Okay, stand like this. Just a moment. Okay, you see this picture. So after deformation, the red line, the red diagonal, red is the deformed configuration, black is before deformation, okay?
Yeah.
So after deformation, the red line still coincides exactly, okay? That
Yes.
means that will happen when this angle and this angle are equal, okay?
Yes.
So subtraction this angle minus this angle, that is the rigid body rotation, okay?
Okay.
So when we have do you remember this thing from mechanics of material that
Yeah, well, I can't see clearly, Doctor.
No.
Doctor.
Okay, let me unshare the screen.
Or do you want me to come to school tomorrow?
No, at least let's get the concept first. Can you see now?
Yeah, the U, the Y, yeah, I can see it clearly, but
That is gamma, right?
yeah.
So instead of the plus, if you put minus there, then that is just rigid body rotation, right?
Yes.
Okay, so let me show you one more thing. Can you compare? Are you able to see both the figures here? This and this?
You mean the difference?
Yeah, the difference. See, in both of them, shear strain is same. But in the first one, there is no rigid body rotation. Second one, in addition to shear strain, this guy is rotated so that the base again falls to the x-axis.
Okay.
So this is shear strain with rigid body rotation, right?
Yeah. Yeah.
Okay, so now it is clear. Now let's go back. Yeah, because tomorrow, I didn't expect. Actually, they asked me to teach this NTSI workshop. So in addition to my class, I have 4 hours teaching NTSI. So it's like too much. And then before they all come, I have to 3D print many things. But now I kind of am not comfortable, little bit better. Like if we design something, by the way, I made in Inventor the sample
Oh,
with diamond and things. So I will make also with the cylinder, the one we discussed, and then we can go print it. And I'm kind of okay with how to print now. So we can print it. Maybe we can print in Ultimaker. That's quite good. Then we can go downstairs, test it, and see what's
no.
going on. So that should be okay. It's just I'm looking for time. That's all. Really.
I think they normally do 3D printing in the library too.
Yeah, we can ask them. So if we make it on the, you mean in the National Public Library or our TSU library?
TSU library.
Okay, we can
They have the
ask them.
machine. They have the machine. They have everything. I've attended one class before, so
You
that's.
mean the MakerBot class?
Is that what?
MakerBot class?
I don't know what type of class they call it, but the one I attended, they taught us how to use 3D to print.
Okay, okay, we can do that too. The thing is that, yeah, that's fine. We can see if their printer is good, that's okay. Our Ultimaker is a very good printer, so because our design is quite complex, right?
Yeah.
So whatever property we get, we want to get it because of the lattice structure. We don't want anything coming because of printing defects, right?
Yeah.
That's the thing. Okay. So now this part is clear. So let's come to angle now. Yeah. So yeah, let me write this one here, then I can. So N is dx ds and bar is dx bar by ds bar. Our angle is n cross n bar. So dx bar is nothing but f dx by ds bar. So n cross n bar. Yeah, we know this one is. You can check out this one while I'm doing this. So, are you familiar with this? Levi's Vita. This one. Yeah, 3D. This one.
Okay.
Yeah, just take a quick look. I'll send you the link on Zoom.
Okay.
Meanwhile, I'm just writing this out. In bar is f dx by ds bar. And cross n bar is just a minute. Okay. So n cross product n bar, that is d. Yes, that's the thing. F is equal to del x. Okay. This is later. Okay. We see it I, J, K. Excuse me. E, I. Oh, yes. Oh, yes. And J and bar K. This is theta I. Yes. Yes, delta theta I. That's correct. Oh, did you know, Ken? Do you remember Mr. Rush was using the Roxless something 3D printer?
So,
He brought one small 3D printer from his home, you remember?
ooh,
Mr. Rush.
oh, he said he has a 3D printer.
He brought one small 3D printer from his home.
Oh, from his home. Okay.
He made it himself.
He made a 3D printer himself.
He built it himself.
Wow.
Yeah, man, he's really amazing. I didn't know that. Like if he has the parts, he knows how to build it.
Wow.
Yeah. Wow.
That's Dr. Gardner that.
Yeah.
Wow.
So, and it's very actually, we are quite lucky because he is very willing to help.
Yes.
You see, many, they know many things, but they will not tell you. They don't want to spend their time in explaining to you.
Yeah, I agree.
Okay. JK, NJ, embarque. Okay, so n bar is equal to dx by ds times ds by ds bar. Dx by ds times lambda, which is f and 1 over lambda. So this is n bar. So n bar k is equal to K J M K. M K is equal to F, yeah, Km and then times 1 over lambda. If Km is then X, X U K M. Lambda. So J J K U K M. Yes, now we will write, we will break UKM into yeah. KM plus omega KM. is like cross product with itself. This is 0. Okay. This one is our answer. This is epsilon ijk in j epsilon kn nm and 1 over lambda plus epsilon jk nj omega kn nm 1 over lambda. Okay, this one you can still see my mouse, right?
No.
Huh? My mouse, this crosshair, you can see?
Yeah.
Okay, so this is the main equation. So there I just change the indices. So I put Q, S, I. Okay, let me write out that what I'm doing and compare it. Q, S, I. Okay. So epsilon Q, S, I. Then it should be NS, yes. Epsilon I. This can be J, yeah, right. J, 1 over lambda plus epsilon QSI minus omega I J and J, yeah, 1 over lambda. Okay, so these two are the ones producing the rotation. Okay, this first part is purely because of shear strain. Okay. Hello, can you?
Yes.
Yeah, this first part, this epsilon QSI NS 1 over lambda delta epsilon ij and j. This is purely because of the shear strain, the rotation. The second part is because of rigid body rotation. Okay, so this will give the total change in angle for our member. Okay,
Yeah.
so in most of our work, we are till now in most of it, we are making sure that, or we are taking care not to apply any rigid body rotation. Okay, it is clear.
Yes.
Okay, just a second. Oh, I just saw your message. Yeah, sure.
Just
Yeah,
send
I
it.
guess you're also tired. Yeah, I'm also a little bit tired today.
Yeah.
Sure. No problem.
We can do tomorrow
I think,
because
see, this is the formula for sure. So we have to see now our formulas. We double check now they are okay.
are you gonna
now,
be available? Are you gonna be available on Saturday?
That's the thing. The Saturday again, night time is okay.
Okay.
But Saturday night I have a long meeting with Dr. Keel. We will start at 11 p.m. and we need to do those documents. But I think we are going to do on Saturday. So then Sunday night should be okay.
Okay, that's fine.
Or Sunday night should be okay.
That's fine. Yeah. Thank you, Dr. Nita.
So okay. But what you need to do in the meantime, see, you have the formula for the strain in each member. You also have the formula for rotation of each member. Okay.
Yeah. Can you send me the calculation, the one you wrote on your notes?
Oh, you mean this thing?
Yeah.
Yeah, sure. I'll send you right. Yeah, I will send you right now. But what I'm saying is that you use these two. These two are exactly from affine. Okay.
Okay.
So you use these two for diamond and reentrant honeycomb, right?
Yeah.
And you check, you have the n direction cosine for every member, right?
Yes.
Right, yes. So you check what is the rotation as per affine. Then you compare that to the geometric compatibility calculation that we did. You know, I sent you the photo during EMI, remember?
Oh, okay. Yeah.
That is the geometric compatibility. According to that, that's how it should be found. Now, according to affine, this is the two formulae. We will get something else, right?
Okay.
They will not match, but we need to force them to match by using strain concentration tensor, right?
Oh, okay. Okay.
You got it now, I think, right?
Yeah. Yeah.
Okay. Okay. According to affine, for every member, we will know the stretch and the rotation from these two formulae, right?
Yes.
But according to the geometric compatibility, we know it's something else. It's not affine, right?
Yeah. We have to force them to work.
That's right. So we have to modify this strain by multiplying it with a concentration tensor so that if you use the modified strain in the affine one, it will match the correct one from
Okay.
geometric compatibility. I think I think now you're clear, right?
Yeah. Yeah. Yeah.
Yeah. So now just do the calculation. Okay. For
Okay.
diamond and for affine. Once you do it by hand and you see all of the differences and blah blah blah, then we can automate it in MATLAB to calculate these concentration tensors for anything.
Okay. Okay. Thank you. Yeah.
Thank you.
Yeah. Thank you.